last class we talked about, and by last class I mean a week ago, we talked about some food. We talked about sandwiches. Does anyone remember what type of sandwich we were making? We were making BLTs. Good. We can remember sandwiches. Let's turn everything in the class into sandwiches. We'll do great. So in a balanced chemical reaction, we have a recipe for how our reactants combine to form products. Remember that our reactants are on the left side, our products show up on the right side. This equation shows how hydrogen and nitrogen combine to form ammonia. So we put in 3 H2s and 1 N2. Given the right conditions and time, 2 NH3s come out. The bonds break and they reform into these new molecules. And so stuff that we can do with this, we can use these coefficients, the 3, the invisible 1, the 2, to convert between any of those 3 chemicals however we want to. For example, if we have 3 moles of N2, underline that, 3 moles of N2, and more than enough H2, so we don't have to worry about H2, how much NH3 can we make? Our question words here are how much. So that tells us we're looking for NH3. So 3 moles of N2, turning that into NH3. We want to look at our coefficients, the N2 and the NH3. We're going to pull those out. 1 mole of N2, if we have that, we could turn into 2 moles of NH3. And we can basically treat this arrow like an equals sign. So 1 mole of N2 is as good as 2 moles of NH3 with a little bit of work put in. So starting with our 3 moles N2, to get rid of the moles N2, we need to put the moles N2 from our conversion factor, our stoichiometry, on the bottom. So we're going to put 1 mole N2 on the bottom. And the 2 mole NH3 we're going to put on the top. So our conversion factor is 2 moles ammonia, NH3, over 1 mole N2. The moles N2 cancel. We do 3 times 2, that's 6 moles NH3. How many moles of N2 are needed to completely react with 7.13 moles of N2? What are we finding in this second problem? We're finding moles of N2. Our question words, how many? And then directly after that, moles of N2. So even though the question's ending with moles of H2, that's not what we're finding. Sometimes we get confused and we think that the last thing is what we're finding. We're finding the moles of N2. The words here, completely react, means that all of our H2 and N2 will get used up. Those are our 2 inputs. Now we care about the H2, so I'll uncover that. So the 2 things that we care about are the N2 and the H2. And I underlined in the wrong color. Switch that. Moles of N2 is what we're finding. We were also given that we have 7.13 moles of H2. So the thing we'll start with, 7.13 mole H2. Our ratio, the purple underlined things, the N2 and the H2, 3H2 equals 1 N2. You can include moles if you want to include moles, if that's helpful. It'll make all of your units cancel out, basically every single cell, every single conversion factor. Or you can leave it off if you're comfortable doing that and you're not going to get confused. You can also leave it off. So I'm showing us the leave it off version. We have H2. We need to put the 3H2 on the bottom. and then the 1N2 goes on the top. So the H2s cancel, moles is still there, and N2 is there now instead of H2. We'll bust out the calculator for this one. 7.13 divided by 3. We get 2.38 moles N2. I think for most of us, since we're in Chem 20, we're relatively new to chemistry, I'm assuming, right? We probably want to include the moles in our conversion factors. That'll just help us with keeping up with our units, reminding ourselves that these coefficients go along with numbers of moles or numbers of atoms, so that we don't accidentally use this conversion factor directly, like starting from grams or something like that. Any confusions about steps that we did here? We love stoichiometry at 9 in the morning. Beautiful. Water forms when hydrogen gas reacts explosively with oxygen gas according to the balanced equation. Helpful keyword here, balanced equation. That means this is already balanced, or at least we've been told that it's balanced, and if it's not, that's the fault of whoever made it. We could also tell that it's balanced. We could assume that it's balanced because there's coefficients. That won't always be the case, but most of the case, people aren't going to be mean and give you wrong coefficients. All right, question, how many moles of H2O, so we've got our question word, how many, and we're looking for moles of H2O, result from the complete reaction of 24.6 moles of O2. So complete reaction here, meaning we're using up all of the O2, we won't have any left over. You can do questions where you're going to have leftover of this. This is not one of those questions. And then we're also told to assume that there is more than enough H2, and that is in there simply because otherwise somebody might say, you didn't say that we had enough H2. I'm the sort of person that would maybe do that. So that's all that is all that is in here. We're good at words. All right. 24.6 moles O2 is what we're starting with. What is our ratio between O2 and H2O?
1 mole of O2 equals 2 moles of H2.
H2O? Yeah, 1 mole of O2 equals 2 moles of H2O. So that invisible 1 in front of our O2, moles O2 equals 2 moles H2O. There's our conversion factor. We have moles of O2, so the 1 mole of O2 is going to go on the bottom. That way it cancels out, and we'll put the 2 moles H2O on the top because we want to get to moles of H2O. Crossing through our moles of O2, we are left with units of moles H2O, and it should be 49.2 moles H2O. We can also add more steps, and we typically are going to have more steps. So we've been looking at mole to mole stoichiometry, which is just one step. Just using our balanced chemical equation, starting with moles, ending in moles. Typically, we're going to start with mass and end in mass, so we're expanding out on both sides. And this is because we can measure mass of reactants, we can measure mass of products. We cannot directly measure moles of things. We have to measure their mass. So what we've been doing is this middle step. We've been going from moles of A to moles of B using our ratio from the balanced equation. We can also add on to this, converting the mass of A to the moles of A, and then at the end converting the moles of B to the mass of B. And we have done these calculations using molar mass. So these steps are not new. It just adds a little bit of a twist. It just adds a couple more steps, but it's not new. We've been doing this, unless I'm taking my crazy pills again. So this chemical reaction, just off the initial look, do we think it's balanced? If we had to guess. Mixed responses, some no's, some yeses. It is, or should be, balanced. And the way that we can immediately guess if it's balanced, we have coefficients. Having coefficients in there typically means it's balanced. It's always a good idea to check, but typically it's going to be balanced if there are coefficients there already. Our question is, what mass of carbon dioxide is emitted by an automobile when this many grams of pure octane is burned? The octane is C8H18. I believe we've seen this in a previous example. So 500 grams of pure octane, and what are we looking for? Mass of carbon dioxide. Our question word what starts our sentence off. So what, and then the thing we're looking for, mass of carbon dioxide. I've told us that our octane is this C8H18. Which of the chemicals is our carbon dioxide? CO2 is our carbon dioxide. So the thing we're going to is the CO2. We don't care about anything else in this example. So we're starting with 5.0 times 10 to the 2 grams C8H18 going to grams CO2. Can we do that in one step? We can't do it in one step because we're starting with grams, we're ending with grams, and to use our balanced chemical equation, we need what units? We need our little furry friends, moles. So we need moles if we're going to use our balanced chemical equation. We have grams, we're going to be ending in grams. We need to add on some steps. How can we get from grams to moles? Molar mass. So we're starting with grams C8H18. We can get to moles C8H18 using our molar mass. We'll have to calculate that. If I remember correctly, it's like 118, somewhere in there. And then from our moles of C8H18, our octane, what can we do with that? What can we do with moles C8H18 that will help us get to grams CO2 at the end?
Can we try to find the atomic mass of C8H18?
We can get the molar mass of C8H18. That's how we're getting from grams of octane to moles of octane. Is moles of octane our final goal? No, it's not our final goal. What is our chemical that we want at the end? CO2 is what we're looking for. Is there something that relates an amount of octane to CO2? Do we have something that shows us how those two are related? We do. Up at the top. Our balanced chemical equation. So that's where this comes in. This is the stoichiometry step. That's what we were doing in the previous slides. So we can convert from moles of octane. We've got 2 octane in equals 16 CO2 out. This is our ratio or stoichiometry step. We can get to moles of CO2. Can we get from moles of CO2 to grams of CO2? Yes, we can. What are we going to use to do that? Molar mass. Also, I was wrong about the molar mass of octane. It's 114. And CO2 is 44 and some change. 0.009 grams per mole. So this is what our solution map is going to look like. This skeleton of our solution map is going to be very similar a lot of the time. If you're starting with one chemical and ending with another chemical, you are going to need a stoichiometry step. I think that's always true. If you're starting with one chemical, going to another chemical, at some point you are going to need to do a stoichiometry step. To do the stoichiometry step, you need to have moles, and you will be going to moles. If you're starting in grams going to moles, we're going to use molar mass. At the end, we're going to use molar mass, but in the other direction, moles to grams. So our first step, we need to get our grams, turn it into moles. We use our molar mass to do that. Our molar mass for octane, 114.232 grams over moles. We have grams. We want to get rid of the grams, so the grams part of our molar mass with the number goes on the bottom. We're dividing by our molar mass. I'll show us the maximum unit version because that makes all of our units cancel out every single step, which is kind of nice. So first step, right, we're dividing by our molar mass. That'll turn grams into moles. So our grams of octane cancels with our grams of octane. We're left with moles of octane. Now that we're in moles, we can use our balanced chemical reaction and our coefficients. 2 octane will turn into 16 CO2. So 2 moles octane will turn into or equals 16 moles CO2. We have octane. We need to put the 2 moles octane on the bottom in our conversion factor. We'll put the 16 moles CO2 on the top because that's what we are trying to find. Our moles C8H18 cancel. Our units are moles CO2. We're following along with our solution map. We're right where we want to be. To get from moles to grams, we need to use our molar mass. Are we going to multiply or divide by our molar mass? We are going to multiply. The reason that we're going to multiply is the 44.009 part goes with the grams, and the moles goes on the bottom. And what this does for us is it lets us cancel out, in orange, go Giants, our moles of CO2. That's COS Giants, not San Francisco or New York Giants, by the way. Do we have any questions or confusions about how we put together the individual steps? I'd like to remind us, you will have to put together these individual steps. On exams, on homeworks, in labs, you can get some help on some of those. Exams, though, you're not probably going to get much help. So make sure that once the homework for this is up, that you take a look at it, give it some tries, maybe ask Logan for help in his SI sessions, or go see Liz or Jonathan during their STEM ambassador sessions in the steam room where the floral lab will be. The answer that we get out is 1.5 times 10 to the 3. This is 1,500 grams with 2 sig figs. Just to show us the non-scientific notation form. This is, again, a really common solution map that we'll see, this mass-to-mass stoichiometry. It's not the only one that we'll see, but it's very common. So it might be worth writing down somewhere this solution map if you're more of the approach where you just want to kind of memorize stuff. This might be a helpful solution map to have memorized, at least the steps memorized. We're going to swap out some of these steps later, but for now, this is our solution map that we're going to be using a lot. Mass of one chemical going to mass of another chemical, and what we're using for each of those steps. One for us to try, using the same formula, what mass of octane would be needed to generate 42.3 grams of water. By same formula, I meant same reaction. I'll give us all of the molar masses so that we can skip that step. It's up to you and the people around you to figure out the rest of the problem. I forgot to mention when I was writing in the molar masses that our octane is our C8H18. We saw it on the previous slide, but I forgot to put it up here. And our water, that's our H2O. So the two things that we care about, the two chemicals that were mentioned, are water. That's going to be our H2O. And then the other thing is the octane, our C8H18. The other two chemicals were not mentioned at all. We do not care about those other chemicals. So if it's helpful for you, you can just cross them out. Get rid of them. We don't need them. Which chemical are we starting with? Which chemical do we have a number with? 42.3 grams of water. That is our starting point. So 42.3 grams of water is what we're starting with. That means the other thing, mass of octane, is what we're looking for. So grams, C8H18. The other way that we could have identified this is our question word. Our question word what up at the front, meaning that the next thing typically is what we're looking for. So we are looking for mass of octane, grams of C8H18. Either of those two ways, as long as you can identify we're starting with H2O, we're going to octane. The question is worded backwards. It feels like it should be going the other way. That's intentional. I did that on purpose, I'm pretty sure, for this slide. Because you will see that shows up on exams, that shows up in the real world, that'll show up on homework questions, not all the time, but sometimes, and so we want to be able to figure out which way is up. So starting with the grams of H2O, our H2O is over here. We need to at some point swap from H2O to octane. To do that, we need to use this balanced chemical equation. And to do that, we need to be in moles. We must have moles to use the balanced reaction. So we need to get to moles first. So we're going to take our grams of H2O and convert that to moles with our first step. That means we're using this 18.015 grams per mole. We're dividing, that turns grams into moles. Because we're dividing, the grams of H2O is on the bottom, that cancels the grams H2O that are on the top. And our units at this point would be the moles of H2O. I'm going to do something I don't normally do, and we'll do it one step at a time. Is that a Demi Lovato song? Or is that Selena? I don't remember. Anyway, not important. 2.348 ... moles H2O. The ... remember, means there's other numbers. It's 2.348043297. We're going to use all those numbers. We're not going to write them down because I'm lazy. But we are going to use them so we don't end up with a rounding error. From our moles of H2O for our second step in our process, we can switch now from moles of H2O, because we've got H2O in our problem, in our reaction. We can convert that to our octane. And we're going to use our ratio of 18 to 2 to do that. So the 18 moles H2O goes on the bottom, so those cancel out. We'll do that with that red slash through. And then 2 C8H18, forgot my moles, goes on the top. People are having a party out there. So multiply by 2, divide by 18, 0.2608 ... moles C8H18. And then with this moles of octane, we can get to grams of octane, and that's with our molar mass, this 114 and change. And that's going to be by multiplying. So times 114.232, and we get out 29.8 with a 0 after it, so we're going to round that to 29.8 grams C8H18. Any questions at all about that? Questions, confusions, contusions, ablutions? I don't even know if ablutions is a word, but it ends in oosians. Ammonium nitrate decomposes to dinitrogen monoxide and water according to the following equation. So this is our ammonium nitrate. This is our dinitrogen monoxide. H2O is our water. In a certain experiment, 45.7 grams of ammonium nitrate is decomposed. Find a command word. Find is a command word. Find the mass of each of the products formed. So we're going to end up with two answers for this question. The thing that we're starting with is the number that we were given, 45.7 grams ammonium nitrate. If we had to guess, is this balanced? It is balanced. Why did we guess that? We checked. The other way that we could guess is that it's got coefficients. Checking is better, but we have coefficients, so we can also assume that it's balanced. Balanced, and we checked. Someone checked. So our 45.7 grams ammonium nitrate going to N2O and also to H2O. So grams ammonium nitrate going to grams dinitrogen monoxide and also grams H2O. Oh, what fun. So there's an easier way to do this. Obviously, so there's two ways that I can imagine us doing this. One of them, you start with your grams of NH4NO3, and you just go all the way through to the end for grams of N2O. You start over, you go all the way to the grams of H2O. We can also get our moles of NH4NO3 and then do different ratio steps. It'll save you the tiniest little bit of work. I'm going to show us that way. What can we do with grams of ammonium nitrate? What might our next step be, our first step be? I'm hearing murmurings of moles. We can turn it into moles. So 45.7 grams, our molar mass, 80.043 grams per mole. So dividing by our molar mass, converts us to moles ammonium nitrate. So 45.7 divided by that number, 0.5709 ... moles NH4NO3. And then we're going to split our path here. So part of the reason we did this is one step and then stopped is so that we could switch for our ratio steps. We can go from NH4NO3 to N2O. We can also go from NH4NO3 to H2O, and then we can convert those to grams at the end. What is our ratio of NH4NO3 to N2O? What to what? 1 mole to 1 mole. We love to see it. So a 1-to-1 between N2O and NH4NO3, that means it's going to be the same number. So we've got a 1-to-1 ratio, 0.5709 ... moles N2O. What is our ratio between NH4NO3 and H2O? 1 to 2 in green. So 1 ammonium nitrate turns into 2 H2O. So we're going to be multiplying by 2. We put the NH4NO3 part on the bottom so it cancels, the H2O part on the top. So we just do times 2. 1.141 ... moles H2O. And then how do we get from moles to grams? Molar mass, are we multiplying or dividing? we're multiplying. The grams and molar mass is on the top, like we see here with our ammonium nitrate. So we want the grams to be on the top so that that's what we end up with. So our N2O, 14.007 times 2 plus just shy of 16. It's so close to CO2. 44.013 grams per mole. Yeah. So those are our grams per mole. It's super helpful, by the way, to have molar mass values for some of the elements we use a lot. It's really helpful to have those memorized. You don't have to, of course, but it's so convenient to just have them in your brain. For this class specifically. For the rest of you, it's probably not that convenient for your daily life, but it comes up for me a lot, as it turns out, because it's my job. All right, so we'll take that. I'm going to do the bottom one first. The 1.14 and change times 18.015. And we get out, rounding for, got to put the numbers in, 18.015 grams per mole equals 20.57. 57. The 5 is our last significant figure, so that rounds up to 6. From our other one, we go back to this 0.57 number. We had a 1-to-1 ratio, and we're multiplying by our molar mass for N2O. 44.013 grams per mole. Moles cancel. The number we get is 25.12. Rounding for 3 significant figures, 25.1 grams N2O. So those would be our 2 answers. That's right. Confusions. I don't expect that I will give you a question where you have to calculate both endings because our exams are multiple choice. But you will definitely have questions that do basically one of these paths. This type of question 100% will show up, like the grams to moles to grams, that solution map 100% will show up on our midterm and on our final. We can also increase the complexity, and this brings us more in line with the real world, and so we're going back to our sandwiches example. Let's say we go and check our fridge, we check the pantry, we check any other place that we might store food. We find we've got 12 strips of bacon, 5 pieces of lettuce, 8 slices of tomato, and 8 slices of bread. And we're very hungry. We want to know how many sandwiches can I make. We have to do some math. So we reference our recipe for how many sandwiches we can make. We've got 12 strips of bacon. How many BLTs could we make with our strips of bacon? 12 bacon. What's our ratio of bacon to BLTs? 4-to-1. 4 strips in, 1 BLT out. So if we put in 4 bacon, we get out 1 BLT. 12 divided by 4, 3 BLT. Does that mean that we can make 3 BLTs if we have 12 strips of bacon? Not necessarily, because we also have lettuce, tomato, and bread. We also have to have enough of those to make the sandwiches. Otherwise, we're just eating 4 strips of bacon at a time, which not necessarily a bad thing. So let's check our other ones. Our 5 pieces of lettuce. We've got 5 lettuce. I'm omitting the pieces part. So 5 pieces of lettuce. Our ratio of lettuce to BLTs is what? 1 to 1. So 1 piece of lettuce, 1 BLT. 1 piece of lettuce in. That could turn into 1 BLT, assuming we have the other stuff, which we don't necessarily. But that means that we can make 5 BLTs with our lettuce. Of course, we have extra lettuce. So we've got the potential for 5 BLTs. Could we make 5 BLTs? If we have unlimited bread, unlimited tomato, can we make 5 BLTs? No, why not? We only have 3 sandwiches worth of bacon, so we're going to run out of bacon first. So the maximum currently that we can make, we currently have enough, we can make 3 BLTs. Let's take a look at our tomato and bread. They have the same ratios and the same inputs. So I'm going to write 8 tomato slash, no, I won't be lazy. We'll do it proper. 8 bread, our ratio 2 to 1 and 2 to 1. So 2 pieces of bread in, 1 BLT out, 2 slices of tomato in, 1 BLT out. So for both of these, the answer is 4 BLTs. Can we make 4 BLTs? No, we can't make 4 BLTs. Why not? We only have enough bacon for 3 sandwiches. So we're going to run out of bacon first. We could make, I don't know if we could call, an LT, a vegan BLT. Probably wouldn't recommend it. Maybe if it's an heirloom tomato, maybe it's tasty enough. Add a little salt, some pepper. Could be good. Some fancy bread. I don't know what we're dealing with here. But the maximum number of BLTs that we can make is 3. We can make 3 BLTs. We can't make 4, we can't make 5, because we'll run out of bacon. Do we have questions about that? The reason that we're talking about it with sandwiches is because we're going to apply this to chemicals. And we're going to, here's the visual of what that looks like. I changed the recipe at some point. So it used to be, I think, 1 slice of tomato, but I thought 2 slices of potato would be better. So if this were a chemical reaction, or bacon, we've got them grouped into 4 strips, we can make 3 BLTs. That's our limiting reactant. So bacon is the limiting, in this case, ingredient for cooking. In chemistry, we call it the limiting reactant. The limiting reactant is the thing that runs out first. It's what's stopping us from making 4, 5, 6, or more BLTs. And then 3 BLTs is what we would call our theoretical yield. So our TH yield, theoretical yield, this is the maximum number we can make, which is really the smallest number that we get out as one of our answers. It's how much we can make with our limiting reactant. let's say that we put together our BLTs. While we're in progress on our second sandwich, our dog steals one off the counter. Straight to jail. Immediately to jail. Right into the kennel. So even though we had enough bacon for 3 BLTs, we finished with only 2 BLTs because I'm not sharing food with my dog, and in this scenario, you aren't either. So we end up with only 2 BLTs out. We only made 2 BLTs. We ended up with 2 sandwiches, not 3 sandwiches. So that was our actual yield. In chemical reactions, we also often end up with an actual yield that is lower than our theoretical yield, because in theory we could have made 3, we only made 2. That also typically happens in chemical reactions, like in the lab. However, it's not usually because a dog is stealing our ingredients or stealing some of our product. It's just other stuff that goes on. Some bad reactant, something went crazy in the reaction process. And so with that actual yield, we can calculate percent yield, and percent yield has this formula. It's our actual yield, how much we made in BLTs, over how much we could have made, the theoretical yield, times 100%. In this case, it's 67%. So again, our formula, percent yield equals actual yield over theoretical yield. And because it's a percent yield, times 100%. Pretty much anytime anything has percent in the name, there's a times 100% in there. So because one of our BLTs was stolen by our dog, who's now in jail, we only got 67% of our theoretical yield. These sort of calculations are really helpful, particularly in the chemistry context, because a lot of times people come up with, hey, I made this new chemical and here's how I did it. They publish that through some big corporation that steals all their money. And then other people can read it by paying them money to read it, the thing that they submitted for free but paid money to do. Politics. But the end result is somebody says, hey, I made this and here's how I made it and here's how much I made, so that when we go and try to do it, we can compare our results with their results. If they're way off, like if we got a much lower yield, then we might, okay, well, what did we do wrong versus what they did? Or we didn't have quite the exact same ingredients, and so we changed one of the ingredients, and we got a higher yield. That could be worth paying a lot of money to have published so that other people can pay to access it too. It basically just helps us set our expectations for the reaction, because some reactions you'll get like a 90% yield, others it might be like a 15% yield. So where if you're expecting 1 gram, you get 0.15 grams out. This is also helpful for cooking and for recipes. Recipes often tell you, here's how much this recipe will make, so you don't have to make it as like a practice and then figure out how much it makes. Like if you have a party that you're throwing, you've got family coming over, you've got friends, awesome, coming over, you can go to the store and buy enough ingredients to make however many batches you need to end up with the right amount of food for your party guests. These calculations also help us. It's just not the chemical calculations, it's these recipe calculations. All right, the actual yield of a chemical reaction must be determined experimentally. It cannot be calculated. On an exam, you will be given an actual yield if you need to solve 4% yield. So it'll be given if you're solving 4% yield. Percent yield shows up on the exam. Actual yield is almost always less than 100% because some of the product doesn't form or some of it's lost when you're recovering it. It stays behind in the flask even though you washed it a billion times, you accidentally spilled some on the floor, your dog ate it, what have you. And then here's the summary of kind of the last couple of terms that we had. So this could be a good reference slide if you want to study or remind yourself what limiting reactant are. The limiting reactant gets used up completely. That was our bacon in our BLT example. It makes the least amount of product. Our theoretical yield is the amount of product that can be made from our limiting reactant. So find the smallest amount that you can make. Trace that back to the start. That's your limiting reactant. That amount is your theoretical yield. That's how much you could make if everything went perfectly, and it's never going to. So what you actually get is the actual yield. That's your experimental yield. And then you can crunch the numbers, actual yield over theoretical yield, typically in grams, times 100%, you get percent yield out. Do we have any lingering questions about stoichiometry, our ratios, or any of the other stuff that we did here? Okay, then we will call that complete.